Why principal component analysis is a machine learning method, but exploratory factor analysis is not. Aloha, everyone. Today, we're going to clarify a common point of confusion when working with data: the distinction between principal component analysis, or PCA, and exploratory factor analysis, or EFA, especially in the context of machine learning. It's easy to mix up PCA and EFA. In many cases, both procedures can generate surprisingly similar results. Specifically, as the number of variables included in the analysis increases, the results from PCA and EFA tend to converge. To complicate matters, some statistical software packages, like IBM SPSS, lump the two together under a broad umbrella known as dimension reduction. When the users select factor analysis, the default extraction method is PCA, not a true factor analysis. This has led to a situation where some authors unwittingly present PCA results when they genuinely thought they were performing EFA. But today, we're going to set the record straight. Let's start with their core definitions. PCA is a technique that transforms your observed, correlated variables into a new set of uncorrelated variables called principal components. These components are ordered by the amount of variance they explain in your data, meaning the first few components capture most of the information. EFA, on the other hand, is a statistical method used to uncover the underlying, unobserved latent factors that explain the correlations among your observed variables. It posits a formal model where observed variables are caused by these hidden factors and unique error. The main difference lies in their fundamental goals and how they achieve them. PCA is primarily a data reduction technique focused on maximizing explained variance and transforming data, without making assumptions about underlying causal structures. EFA, however, is a model testing and theory-driven approach that seeks to validate a theoretical model of latent constructs and their relationships with observed variables, requiring specific statistical assumptions. Now, why is PCA considered a machine learning method while EFA generally isn't? PCA is a data-driven algorithm that fits perfectly into the machine learning paradigm of unsupervised learning. This aligns with the philosophy of data mining. Let the data speak for themselves without imposing preconception or post-hoc transformations. It's frequently used in machine learning workflows for practical tasks like dimensionality reduction, making datasets more manageable, noise filtering, by focusing on the most informative components, and feature extraction, creating new, useful features for predictive models. PCA operates without relying on theoretical assumptions about latent structures or specific error distributions, making it a flexible tool for discovering patterns in unlabeled data. You'll find PCA readily integrated into standard machine learning libraries like scikit-learn and TensorFlow because it aligns directly with the goal of extracting structure from raw data. In contrast, EFA is rooted in the statistical modeling tradition. It is based on a formal factor model that partitions variance into common and unique components, often involving assumptions like multivariate normality and rigorous model fit testing. EFA is not typically designed for predictive modeling or generalization beyond the sample. Instead, its focus is on understanding the theoretical relationships between latent constructs and observed variables. This distinction in purpose and operational framework is why PCA is conventionally classified as an unsupervised machine learning method, while EFA remains a specialized statistical modeling technique. So, how does PCA really shine in data science and machine learning? Let me give you a few vivid examples. Imagine you're working with a massive dataset of images, like in image recognition. Each image might have thousands or even millions of pixels, and each pixel is a feature. Training a machine learning model directly on all these pixels would be computationally insane and prone to overfitting. This is where PCA comes to the rescue. We can apply PCA to reduce those thousands of pixel features down to a few hundred principal components, capturing the most important visual information while drastically speeding up training and improving model performance. Think of it like distilling the essence of an image. Or consider anomaly detection. Let's say you're monitoring a network for unusual activity. You have tons of metrics, data transfer rates, login attempts, packet sizes, you name it. A normal network might have these metrics fluctuating in a predictable pattern. But an anomaly, like a cyber attack, might cause a subtle shift across many of these metrics simultaneously. PCA can help us here too. We can project all these metrics into a lower dimensional space using PCA. When a new data point comes in, if it falls far away from the clusters of normal data in this reduced space, it could be flagged as a potential anomaly. PCA helps us see these subtle deviations that would be lost in the noise of high-dimensional data. Another fantastic use case is in genomics and bioinformatics. Imagine studying gene expression data, where you have thousands of genes and hundreds of samples. This high dimensionality makes it incredibly difficult to find patterns related to diseases or drug responses. PCA can be used to reduce the dimensions, allowing researchers to visualize gene expression patterns in 2D or 3D plots, revealing clusters of samples with similar genetic profiles or identifying key genes driving differences. It's like finding the hidden story in a sea of genetic information. And finally, consider customer segmentation in marketing. You have data on customer demographics, purchase history, website interactions, dozens, if not hundreds, of variables. To effectively target customers, you want to group them into meaningful segments. PCA can help reduce this complexity by transforming these many variables into a few principal components that represent underlying customer behaviors or preferences. These components can then be used in clustering algorithms to create distinct customer segments that are easier to understand and target with personalized campaigns. These examples highlight how PCA isn't just a statistical trick. It's a powerful, versatile tool that directly enables and enhances machine learning applications by making complex data more manageable, insightful, and actionable. What's your take? Do you lean more toward PCA or EFA, and why? I love to hear your feedback. Drop your thoughts in the comments below. If you found this helpful, don't forget to like, share, and subscribe for more insights. Thanks for watching. Mahalo.